Chapter 11 is on intermolecular forces and liquids/solids, which is appropriate because at the end of chapter 10, which is on gases, we talk about when the gas laws break down. Now that happens, so things stop acting like gases when we either have really high pressure and basically all of the molecules are forced to be really close together, so they start to stick together, and also when we have a really low temperature, so really cold. So at those conditions, we transition from the gas phase into when the molecules are all touching, which is the liquid phase. When they are interacting with each other, they experience some kind of attractive force. When that happens, they're going to be held together. So the forces that hold atoms and molecules together are called intermolecular forces, and they're the attractive forces that exist between molecules and atoms. Inter meaning between. Intramolecular would be like covalent bonds. So they are what helps condensed phases be condensed. If not, everything would be spread apart and everything would be in the gas phase. So thank you, intermolecular forces, for us to have other phases other than gases. So whether we end up being what a solid, liquid, or gas will depend on how strong the intermolecular forces are between the particles. So when we have a lot of thermal energy or a high temperature, things tend to be gaseous because they're moving around quickly and can break apart from those forces. When thermal energy is low, so low temperature, we have a less amount of energy, so they tend to be liquid or solid because they basically are going to be stuck together. So that gets into that gas breakdown. We're at low temperature, low thermal energy. So here are some properties of our different states. So gases have low density because they're far apart and take up the whole volume. They have an indefinite shape, so they just take up whatever volume they're in. They're weak intermolecular forces in general. Liquids have higher density, as do solids. Liquids have indefinite shape, so they take the shape of their container, where they have the same volume, so they're not compressible. And solids have a definite shape and volume, so stronger intermolecular forces. So definite means that it's going to keep its shape when we put it in a new container. So a solid would do that, right? And indefinite means it's going to take the shape of the container, like a liquid or a gas would. So some just general things about liquids. They're close together, but they're not so close together that they can't move around. So they still are able to flow and fill up the container. They're incompressible, so if I apply a force on it, the volume's not going to change, right? They're close enough to where we can't really squish them that much closer together. They're able to flow, but they have enough, so they're moving, but not enough so that they can escape from the container, so they can't break apart. They're stuck together much more. They have high densities because they are close together, and definite volume because they are close together as well. So they're unable to escape into the gas phase. They're basically stuck next to their neighbor. Gases have complete freedom to move around in any direction. They are bumping into the container and each other, but they don't stick together. So they bump and they move on. So because of that, they can expand and take up the shape and volume of the container that they're in. There's lots of space in between the gases. That's what makes them a gas, making their molar volume and their density really low. Their molar volume, so the amount of space they take up is really high, so their density is lower. And they're compressible, so if I put some pressure on a liquid, it's basically at the same volume, but I can put some pressure on a gas and squish them closer together, so my volume's going to go down and my pressure will go up. So they are able to be compressed. Solids are kind of like liquids where they're next to each other, but have such a high attraction that they don't really move at all. So they don't flow. They're in a fixed position. They just vibrate. They are incompressible, just like liquids, because they're so close together already. If anything, they're more incompressible than liquids. They are not static. So basically, they're just being able to vibrate around. So because they are so stuck together, they take the shape of their container and their volume, so they don't flow at all. When they are ordered in an orderly way, they're crystalline shape. So with different ionic compounds, and diamond would be very ordered. When they have no order or pattern, they're called amorphous solids, so lacking a shape. So plastic and glass are examples of that, and we'll talk about that more in chapter 12. So how do we go between the different phases? Well, if I want to get ice to become liquid, I can add heat. If I want to get liquid to become ice, I cool it down. So I can change the temperature by either heating or cooling. If I also want my gas to turn into a liquid, I could add pressure, squish them close together. Or if I want to turn my liquid into a gas, I could lower the pressure or expand the volume. So we could also do it by changing the pressure, be going between liquid and gas. So when we do this, these are all physical changes. We're not changing the composition of the material. All we're doing is changing the phase that it's in. So physical change. So here's an example of liquid water. Which one would be the water vapor after you boiled it? So we should still have water molecules. So still should be H2O. Well, here's H2 and O2, and here's H atoms and O atoms. So this is the only one that has water molecules still intact. Okay, so what are the forces that hold them together? So we have the IMFs. We talked about intermolecular forces. I'm going to call them IMFs. The different intermolecular forces that a molecule has will be due to its structure. And the stronger that the forces, the higher the boiling point. So boiling point and melting point are a way that we can kind of measure or get a gauge of the strength of the intermolecular forces of that compound or material. So that's what you'll often see, that we'll be comparing different melting and boiling points to help us get a better idea. Now, what's really important when we do that is we're comparing similar things. I'll talk a little bit more about that in a minute. So when I boil a liquid, I have to basically go from a liquid phase to a gas phase. So I have to give it enough energy to break it from its neighbor, but not so much that I break the covalent bonds. Okay, I'm not trying to do a chemical reaction. I want to just do a physical reaction. So you'll notice that these phase changes require a lot less energy. So a lot less energy than a chemical change, because we're not actually breaking covalent bonds. So there's a variety of strengths, kind of like a spectrum, and it depends on the particles that you're using, what kind of molecules or atoms are there. The stronger the forces, the higher they're going to be stuck together, so the more they're going to resist moving. So basically we think about a strong magnet, right? It's harder to break apart when it has a stronger charge. But when I have a weaker charge, I can pull it apart easily. Great. So how does this work? Well, we're going to have molecules that are attracted to each other. They do this by having opposite charges. So positive and negative sides will attract. Now, a positive ion will attract a negative ion, so that is when we have ionic bonds. We've already studied that, lattice structures and all that fun stuff. But even when we have in a molecular compound like water, If it's a polar molecule, then it will have a positive dipole and a negative dipole. And between two molecules, there will be an attraction of positive and negative and a repulsion of like charges. And even nonpolar molecules can have temporary dipoles, and we'll talk about that. So the larger the charge, the stronger the attraction. This is based on that equation, the energy equals the constant times charge 1 multiplied by charge 2 over the radius. I love this equation. So if I have really high charges here, then I'm going to have a higher energy, right? It's going to have a higher force. I also could have longer distances, so a big radius, and I will have a weaker attraction. Or I can say that if I have a closer together, so the radius, small number here, then I would have a stronger attraction. So it's dependent on kind of what it's being made out of. And keep in mind, these are small compared to intramolecular forces or bonding, having to do mostly with the charges being a lot smaller with dipoles. And we have them further apart than in a bond. The three types that we're going to learn about are dispersion forces, and those are the temporary ones. The permanent dipole ones are called dipole-dipole, and a very strong dipole-dipole is called hydrogen bonding. So let's talk about each one individually. So dispersion forces, let's go over to the side real quick. So let's say we have a helium atom. And for one moment, so helium has 2 protons in the center, and it has, so I'll put a +2 here, and it has 2 electrons that are orbiting or moving around the 1s orbital. And at any one given moment, it's possible that 2 electrons could be on the same side, just briefly, instantaneously. So for that brief second, I would have a partial negative on that side due to the electrons both being on that side. And meaning on the opposite side, I have a partial positive. So if it happened to be near another helium atom, then that negative dipole there is going to push the electrons of the other atom over here, creating another dipole, just in time for that to move, and now this has another dipole. And we have a positive dipole over here, and so on. So it kind of has this chain reaction. So because we can have fluctuations in the electron distribution, we can have a temporary dipole. So that's where we have a region with excess electron density, so electrons happening to be on one side, giving it a negative side. And then, therefore, the other side of the atom or molecule would have a partially positive charge. So we call these London forces, dispersion forces, London dispersion forces, sometimes van der Waals forces. I call them LDFs for London dispersion forces. So this basically induces a dipole in surrounding molecules. And because of that, I wouldn't call them the weakest, I would call them temporary. Sometimes actually dispersion forces can be stronger than our permanent dipoles, so we'll talk about when that happens. Every atom and molecule, if it has an electron, it can do a dispersion forces. And the more electrons we have equals higher possibility for this distribution, uneven distribution, so higher LDFs. So let's go into the next slide. So the biggest things with LDFs are the size and shape. So when we have atoms or molecules, as the molar mass of those goes up, we're going to get more electrons. And so as we get more electrons, we're going to have more polarizable cloud or more ability to fluctuate where those electrons are. So we're going to have an increased strength of the LDFs. So if we look at something like the noble gases, now they are all just single atoms, no bonds or anything. And as the molar mass goes up, their LDFs go up, and we can see that by measuring the boiling point. Higher intermolecular forces means higher boiling point. Okay, so right there we can see that. The last thing, so mass, that's a big one. The next thing is the shape. So with shape, even if I have a molecule that is exactly the same molar mass, so such as N-pentane, so we have C5H12 here and here. The only difference here is how they are organized. So in this N-pentane, it's a long chain. So it has a really high surface area. So a lot of possibility to have contact or interaction between its neighbor if they are laying down on each other. Here in neopentane, it's like a sphere, so it has a really small area where they can be interacting. Because of that, this large area allows for more polarizability of the electron cloud, and therefore it's going to have stronger LDFs. So higher surface area equals higher LDFs, and we'll see a higher boiling point. So here it's 36, where here for neopentane is 9.5. So if I wanted to compare, I wouldn't want to compare molar mass, like a molecule with a different molar mass, to something that's spherical versus a different molar mass that's flat. I really want to be comparing the same thing. So here I'm comparing increased molar mass, but they're all the long chains. And we can see that increase in the boiling point, so higher LDFs. So make sure you're comparing similar things so that way you only have one variable that's changing. The next one is dipole-dipole. Now this happens when I have a polar molecule. Now if you do not remember how to determine if a molecule is polar or not, you need to go back into, I want to say chapter 5, talking about polarity, and really dig into those considerations. As a reminder, molecules that are non-polar are going to have all terminal atoms the same, and no lone pairs on the central atom. Okay, so same terminal atoms, no lone pairs for the most part. That's the rule. If it meets that criteria, it's nonpolar. If it doesn't, it's polar. So polar molecules have a permanent dipole due to their structure, meaning that there's going to be one side that has an electron-rich area and one side that's electron-deficient. And so here's an electron-rich here, and therefore an electron-deficient. And so there's going to be an attraction between those molecules. This makes it stronger as long as there's similar size and shape. So if we're going to be comparing formaldehyde and ethane, it's important that their molar masses are very similar, so that way we're comparing apples to apples. So we can see formaldehyde, believe that's it, right? Nope, that's not it. It's right here. Has a electron or an oxygen atom here, so very electron dense, where here it's electron deficient. So that permanent dipole means its boiling point is going to be much higher than ethane, which is a polar or non-polar molecule. Also, if you see molecules that have just carbons and hydrogens, very non-polar. Okay, so here's a very non-polar molecule. Similar mass, but because of that dipole in formaldehyde, its boiling point goes up. Here we have molecules that are very similar in size and kind of close in shape. And you can see as the dipole grows this way, its boiling point also grows up. So just again showing that as we get more polar, we're going to have a higher IMFs because of dipole-dipole interactions. Okay, so which of these have dipole-dipole forces? So we're going to draw them. I want you to pause your screen, pause it right now, and then focus on just drawing them. Then come back in probably about 10 seconds. I'll have the shapes on the board so you can compare the shapes, and then about 10 seconds later I'll have the answers. Okay, here are the Lewis structures for these different atoms. So take a moment to correct and then determine what the intermolecular forces are for those. Okay, here you can see carbon dioxide is nonpolar, so it's just going to have LDFs, no dipole-dipole. Dichloromethane is polar because it has two, even though it looks like the chlorines cancel out, it's really in three-dimensional space, so it doesn't. So it is polar, so it'll have LDFs and dipole-dipole. Methane is nonpolar, so it'll just have LDFs, no dipole-dipole. Dichlorosulfide or sulfur dichloride is polar because of the lone pairs here, and so it has LDFs and dipole-dipole. Chloromethane is polar, so it has LDFs and dipole-dipole, and hydrogen chloride is polar, so it has LDFs and dipole-dipole. Notice everything has LDFs, so when in doubt, always put LDFs. Everything will always have that. Then check the polarity. Okay, so hydrogen bonding is the next type. So hydrogen bonding happens when we have a super electronegative atom that also happens to be small, bonded to a hydrogen. When that happens, we get a big pull of electrons toward it, causing it to have an extra, basically expose the hydrogen's nucleus. So the most electronegative atoms, we know fluorine is the most electronegative, and then oxygen and nitrogen. They are also really tiny. So when I have hydrogen bonded to a fluoride, hydrogen bonded to an oxygen, or hydrogen bonded to nitrogen, I'm going to have hydrogen bonding only. So H or HF, HO, or HN. Now, hydrogen needs to be directly bonded to it for this to happen. So hydrogen only has one electron. So when its electron is pulled away by these really electronegative atoms, the nucleus is basically super deshielded and vulnerable, leaving it to be ultra positive dipole. So because of that super positive charge, other electron clouds from its neighbors are strongly attracted to it, causing this super strong pull. So we can see it's like super red here and almost like purple. So that means very, very positive or electron deficient. So hydrogen bonding is not this bond here with hydrogen and fluorine. Hydrogen bonding is between two molecules. So if I have hydrogen and fluoride here, that's not the hydrogen bond. The hydrogen bond is between the fluorine of one atom and the hydrogen of another. So that's where we get that strong interaction. So the only things that will form hydrogen bonds are HF, HO, and HN, like I said. So here I see an oxygen with a hydrogen there. So that molecule is going to be able to do hydrogen bonding. So there will be partially positive, strongly positive. This will be negative. And so the hydrogen from one atom or one molecule will hydrogen bond with the other one. This will have an ultra high boiling point compared to its neighbors. But keep in mind that this is an intramolecular force, not an intramolecular force. So it's not as strong as a chemical covalent bonds, only about 2 to 5% for hydrogen bonding, which means those other IMFs are even weaker. So here's an example of ethanol. So we have an OH group there, and dimethyl ether. So same formula, the only difference is where the oxygen is placed. Here the oxygen is connected to carbons, not hydrogen. So this one's it's polar, so it'll do LDFs and dipole-dipole, but this one can do LDFs. It'll also have dipole-dipole, and because it has an oxygen and a hydrogen, it will also do H bonding. So same molar mass, but see a significantly higher boiling point and melting point. You can see this here. Notice the only difference between this carbon and its following groups is that what is bonded to it. So we have the carbon group, and then silica is below it on the periodic table, and then germanium, and then tin. So we're going down. So we're increasing the mass. So we're increasing the LDFs. They're all nonpolar, so it's just LDFs. You can see as it goes up, it's going to have a higher boiling point because of higher LDFs. We see this too with the group below oxygen. Here, they're all polar, so they have dipole-dipole, but they have the same shape. So the only difference here is basically not the polarity, but a huge shift between the mass. So we're having higher LDFs, so going up linear. But notice water has a significantly higher boiling point compared to its its peers, I guess you could say, and that's due, or its group and family, and that's due to the hydrogen bonding. So the IMFs due to LDFs from methane's group. So increasing because of higher molar mass. Polar molecules, so the hydrides are group 5 through 7. They have LDFs and dipole-dipole. But because of the hydrogen bonding that can happen between NO and F with hydrogen, that second row is going to have like an outlier with our boiling points being super high for our hydrogen bonding molecules. The last one I'll talk about is ion dipole attraction, and this we'll focus a lot more on in chapter 13 with solutions. So basically, when we have a ionic compound such as a salt, where we have a negative and positive cations and a lattice, they're in the solid phase. We're very familiar with like salt or chalk being in the solid phase. But we can put sodium chloride in water and it will dissolve, so we can break those ionic compounds, and that has to do with ions being attracted to dipoles and breaking apart. So if I have water like this, we have a negative side and a positive side. So on the anions, water is going to attach to it and basically attack it and pull it off and then get it to look like that. So we'll get a dipole attracted to an ion. And here with the cation, we'll have the negative side of the water attached to that and pull it off. Okay, so these examples, which of these compounds is liquid at room temperature? Things that are more likely to be liquid instead of gas is due to higher intermolecular forces. So here we have, they all have LDFs. Now this molecule is polar, so it'll have dipole-dipole, but it will not have hydrogen bonding because the oxygen is not bonded to the hydrogen. Here it's polar, so it'll also do dipole-dipole, but again, fluorine is not bonded to a hydrogen. Here, hydrogen peroxide, I have 2 hydrogen bonds, or 2 possibilities for hydrogen bonds. So this guy will be likely, it has the strongest intermolecular forces, so likely to be a liquid. And which of these has a higher boiling point? HF or HCl? Well, HF can do hydrogen bonding, where HCl can only do dipole-dipole. So HF, because of its dipole, or because of its hydrogen bonding. Okay, here's just a summary. Dispersions, I won't say they're weakest. They're most temporary. They're weakest if other things are comparable. Everything has it, molecules and atoms, and it can go up with higher molar mass and a long chain-like structure. Polar molecules have dipole-dipole. Hydrogen bonds are the strongest type of dipole-dipole. It happens when nitrogen, oxygen, or fluorine are bonded to hydrogen directly and has a really strong high boiling point, melting point. An ion dipole happens with an ionic compound and polar molecules. This is actually the strongest, and it helps us to have aqueous solutions with ionic compounds. Here's a nice little summary sheet that we got from the textbook with talking about what we just talked about. Okay, some properties of intermolecular forces. First one is surface tension. This is basically the tendency of liquids to minimize surface tension. Or surface area, sorry. So this will specifically happen on the surface layer. This is because when we have a liquid, there's going to be intermolecular forces happening in all directions in the middle. But when we get to the surface, there's not any atoms on top to help balance out the pull. So what's going to happen is you're going to have a net pull down. That's going to cause the surface molecules to tighten up, and you get this layer of tension that's higher at the surface than it would be below. The higher the IMFs, the larger the amount of surface tension. This is basically measured like how much energy you need to increase the surface area by an amount of area in meters squared. So the surface tension of water is 72.8 millijoules per meter squared. Where for benzene, which is nonpolar, is 28. So you can see as I have higher IMFs in water, because it has hydrogen bonding, has a higher surface tension. The way that we can adjust the surface tension is to raise the temperature, because then we can basically you get the molecules to move around a lot more, so you're able to break that tension due to the increase in kinetic energy. Some animals and some of these properties, like putting certain types of items on top of high surface tension liquids, are pretty cool, or like certain bugs that can walk on water. That has to do with them having the appropriate like surface area on their body to help them minimize their pressure that they apply on the surface. So pretty cool. Viscosity is another one. We think of something being really viscous like honey or marmalade, but the technical definition is the resistance of a liquid to flow. So not wrong, something that's really viscous, just really sticky. So it's measured in poise, which is a gram per centimeter second. Weird unit, don't worry about it. But basically, higher intermolecular forces mean that we have a larger viscosity. And that's just because they're more attracted to each other, they're going to be harder to move. So the spherical molecular shape means lower viscosity because they're able to roll and less surface area contact. We can, so here we see molecules getting bigger. They have a higher molar mass, so their LDFs are going up, and you can see the viscosity also goes up. But what I can do is raise the temperature, and that gives the molecules more kinetic energy, and they're able to flow more past each other because they're moving more, and so they can kind of overcome those attractions. Capillary action is related also. This has to do with the ability of a liquid to flow up a thin tube against gravity. The thinner the tube, the higher the capillary action. So what happens is we have two competing forces, cohesive between the molecules, so think like intermolecular forces, right, are cohesive. Adhesive is the intermolecular forces between the liquid and the surface of the tube. So the cohesive forces hold the molecules together within the tube. The adhesive forces drive it up the tube. So we can kind of look at what the shape of the meniscus looks like to figure out who's stronger. So here I have water inside silica tubing. Silica has a lot of oxygen atoms, so a lot of potential for dipole-dipole and hydrogen bonding. So we can see there's a lot of adhesive forces because the meniscus looks like this. So they're able to rise up. Where here I have mercury, and it is convex, so it has a lot of cohesive forces, but it doesn't really have a lot of attraction here. So the meniscus shape is having to do with who's stronger, cohesive or adhesive. So for water, it's concave because water's adhesion to the glass is stronger than its cohesion to itself. Where mercury liquid has a lot of cohesion that's stronger than the adhesion to the glass. So because metallic bonds are stronger, it's a type of bond, not IMF. So that's stronger than intermolecular attractions. Perfect. Now we get to talk more mathematics.